So we are continuing our discussion on the binomial distribution. And as I referenced in the last video, this is an extremely important topic that is on the AP test virtually every single year. It's always on the test somewhere, multiple choice or free response, but it's almost always a focus on the free response section as well. Out of the 6 questions on the free response, one of them is always a probability question, and they like to put a binomial question in those problems. So this is a topic that I feel very good predicting for whatever year you're taking this class. There will be something on the binomial distribution on the free response section. So it's a really good topic to be able to master. We're going to hit some of the highlights from last time in this lesson, and we're going to learn a few shortcuts as well with our calculators. So there was that whole formula that we used the last time, the n choose k, that whole thing that we've got off our formula sheets. But actually, our calculator can do a lot of the same stuff, and it's kind of handy to be able to use that rather than punch out the whole formula like you see left over on my screen right here. So what we're going to do is actually go to the distribution menu, the same place we've seen normal CDF earlier on in the class. All these other options you can see right now we're eventually going to learn about. We're not there yet though. But if you keep on scrolling down, there are 2 options right here for binom PDF and binom CDF. So you might remember with normal problems, C stands for cumulative, which was going to be like less than or equal to, and that's the one we always chose with normal. With binom, we are also going to use PDF. P stands for probability density function. It is used when it's an equals problem. So if you see a problem where they want an exact number, you will use PDF here. We never use normal PDF, but we do for discrete variables use PDF. And then if you have something where it's a less than or equal to problem, you're going to use CDF. Now, if I click on my CDF option right here, with normal CDF, you got to set a lower and an upper. So you just told it exactly what you wanted. If you have a fancier calculator like the TI Inspire, I believe you actually do have an option for a lower and an upper yourself. But on the TI-84s, you can't specify the lower and upper. All it does is it gives you an X value right here, and it assumes that you mean less than or equal to. So if I want less than or equal to 5, let's say I have 20 trials, probability of success is a 0.4, and I want less than or equal to 5, I would do an X value of 5 right here. And then it'll just calculate it for me, and it's really kind of handy. So it's a good trick, but you have to understand that its defaults to, it always does less than or equal to on our basic calculators. So yeah, let's go ahead and practice this in an example. So go ahead and read this problem to yourself here and get your head wrapped around the context. Hopefully a cautionary tale that you guys won't fall into this trap in a couple of weeks when you're taking your final semester exam for me. But you just totally forgot you had an AP Stats final. My final has about 20 multiple choice questions on it, each one with 5 answers. And because you didn't study at all, you just remember nothing, you're panicking, and you just have to straight up guess on every single problem on the test. They do say going in that you assume that one answer is independent of the others. So then they just start talking about probability. Nowhere on this slide does it say the word binomial. And like I said in the last lesson, if you see a probability question and you're like, I don't know how to do that, ask yourself if it's binomial. And frequently it actually is. So it's time to verify our 4 conditions really fast right here. Binary, yes. I'll just talk about it here. Yes, it's binary. You either know how to do it or you don't, or you either get it right or you don't. So that's cool. Independent, they straight up say it in the problem. Number of trials is 20. And the probability of success, if there are 5 options, is going to be 1 out of 5. So it's binomial. So I'm going to set up a variable for this problem. X is going to be the number of correct answers by guessing. And X is binomial, N is 20, P is 1 over 5. So they ask, what is the probability that you get exactly 3 out of the 20 correct? Or in other words, what's the probability X equals 3? By the way, I've been defining the variables, but I just want to emphasize again, on a problem like this, if you start talking about X and you didn't define X, you will lose credit. So make sure you actually define your variable. That's an important step in doing these. So we could do our formula for this, or we could just use our nice new calculator option here. So on my calculator, I want equal to 3. Since it's an equals problem, I'm going to do PDF, not CDF for this one. There are 20 trials, that's n. Probability of success is 1 out of 5, or I could do a 0.2, and my x value is exactly 3. And then you just do it, and it gives you the answer a little easier than having to use the formula. So it's like 0.2053. But when you do these, just like with normal CDF, you have to show your work. We did a binom PDF. First thing it asked us for were trials. We did 20 trials. We had a probability of success of a fifth, and we had an x value of 3. You have to write out your little command. You have to label each part just like you would do on a normal problem. All right. Next up, what is the probability that you get less than 6 questions correct here? So x is less than 6. The issue with this is that I told you guys when you do binom CDF, it always assumes less than or equal to. If you do just a less than, go in and type in a 6, it's going to think you mean less than or equal to, and that will mess your answer up because this is a discrete random variable. So what you got to do is think about this counts 0, 1, 2, 3. All of these numbers are the good ones right here. So if I want less than 6, I'm just going to do an x value of 5 instead. This is the same thing as the probability x is less than or equal to 5. Now these ones, the calculator is sort of handy right here, but it's super handy on this problem because I would have to find 6 different things, do my formula 6 times, which is awful, or I could just do a one-time binom CDF here. My trials are still going to be 20. My p is still going to be a fifth. My x value is going to be a 5. And again, when you type this in, remember this is CDF, not PDF for this one. I'm going to go back. I'm going to do a binom CDF. Trials is 20. Probability of success is a fifth. My x value is 5. And then you get 0.804. So let's appreciate for a second what this is saying right here. If you don't know what you're doing and you just straight up guess on every single question blindly, there's an 80% chance you don't even get 6 questions right. You get 5 or less. Okay, so that's what the math says. And then for this last one here, they ask about the probability that you get at least 12 questions correct. That's greater than or equal to 12. Binom CDF always does less than or equal to, always, on our calculators. So we have to be able to turn this problem into a less than or equal to problem, which will mean that we're going to do a 1 minus on our answer. So I find it helpful on these problems to write out the numbers that you actually want first. Greater than or equal to 12 is everything from 12 all the way up to 20. So if you think about what I do not want then, I don't want everything below 12. I don't want 11, I don't want 10 or 9 or 8, all the way down to 0. So what I'm going to end up doing here is I'm going to do a 1 minus, and I'm going to do 11, because that's the beginning of what I want to cancel out right here. So what I'll do is I'll set it up with a 1 minus. You can do it separately or just all at once. 1 minus, I need to do a binom CDF again. And my x value for this problem is going to end up being an 11. So if I do that with the 1 minus, it's a really small answer right here, 0.0001. So again, talking about just your odds of passing and stuff like that, if you don't know what you're doing on any of the questions here, you don't study at all, you just have to blindly guess, the chances that you even pass out of 12 out of 20 is a 60%, almost 0. Extremely unlikely for that to happen. When you do problems with greater thans and greater than or equal to's, I recommend you take this list approach because it makes it so you pick the right x value. It's very easy to trip up on what's going on. One more comment on this page before I move on. Let's say instead of a greater than or equal to, this was just a greater. In that case, we would not want 12. It would start at 13. So I would do an x value. 12 would be in the no list. So I would do an x value of 12 if it was just greater. So it's best just to write down the list of numbers and use that to help guide your answer. So yeah, that's definitely a lot better than having to use the formula I taught you last time. So now we're moving on, and we're talking about the formulas for the mean and the standard deviation of a binomial random variable. So if x is a binomial random variable, the mean of x is going to equal n times p. So let's think about this logically. I'm not going to prove either of these formulas, but I'll at least try to tell you something for this one right here. In my multiple choice question thing, I had 20 questions right, and the probability you get a question right by guessing is a fifth. 20 times a fifth is 4, so it seems reasonable that this would be a good, like an appropriate average number of questions people will get right. You have 20 questions, you expect to get about a fifth of them right, which is 4. So that formula actually isn't bad. You just take your sample size times your probability of success, and that's the mean. The standard deviation is on your formula sheet, as is the mean, actually. So you don't actually have to memorize either of these, which is nice. Let me show you where those are at. We already learned our main formula right here. They're written down n times p, like I just showed you. And then you have this guy right here for your standard deviation. Our textbook does a nice job explaining this formula if you are curious and want to see, but I'm not going to go into the justification of it, just it's there for us to use. So we have the square root, np, and then 1 minus p, all underneath that square roots. So that is going to be our standard deviation formula for a binomial problem. Both of these only work when your variable is binomial. So let's practice this in the context of our thing that we just did with the exam questions. I actually already spoiled the answer for the mean. What I would do is I would just do 20 times a fifth, which is 4. And then for my standard deviation, basically just plugging and chugging right here, n times p times 1 minus p, or you could write 4 over 5 right there, and then you just plug and chug on the calculator to get your standard deviation. It says to interpret here. I think I'm going to talk about that, but not actually write them. So you guys can write them if you like, or just kind of listen to my interpretation here. We already learned how to do this in section 6.1. So this is going to be just a nice little quick review right here. Over many sets of 20 question multiple choice tests, so you have to have that idea of many trials for the mean, we would expect kids to get an average of 4 questions correct if they just blindly guess the whole time. And then for the standard deviation, a randomly selected students, we expect their score to vary by about 1.78 from the mean of 4. So the typical distance from the mean is your standard deviation. So those are your nice interpretations here. How often will the number of questions guessed correctly be within 1 standard deviation of the mean? Now, this brings up a really bad thing that happens on the AP test sometimes, where people just say, oh, it's normal, it's 68%, that's 1 standard deviation. But you don't know anything about the binomial distribution and the normal distribution yet, so you can't just say 68% and done. What you would need to do, and in the interest of time, I'll tell you how to do it, but I won't actually calculate this right here. Within 1 standard deviation of the mean means you go up by 1 standard deviation, which is like 5.789, and you go down by 1 standard deviation, which is going to be like 2.2 something. So basically, if you score within 1 standard deviation of the mean, you are between these 2 numbers right here. X is binomial, though, and binomials have to be a whole number. So what whole numbers could this be? This could be, can't be 2. 2 is too low. It could be 3, it could be 4, or it could be 5. So what you need to do in this scenario is just find these ones separately with binomial PDF and just add those probabilities together. And you can get your answer that way. I won't go over that because I think you guys are hopefully feeling better about how you actually use the calculator now. But that's what you would do. So in the last video, I referenced sampling without replacements. And it turns out that when you conduct surveys, you're pretty much always going to be doing them without replacement. Talking to the same person twice is silly, and you wouldn't ever do that. So there wouldn't be a good reason to do that in most scenarios here. So anytime you're doing a survey, you're technically not independent from one trial to the next, okay? Because you took one person out that you're not going to pick again. But it turns out that if your population is big enough and your sample size is small enough with respect to your population, it's not a big deal if you don't put the person back. Okay? That's probably confusing. Let me reword. If I'm picking people out of this classroom, typical class for AP Stats is like 15, 18 kids, somewhere in that range. So let's say the probability that you get chosen, or that I choose like somebody with brown hair out of a class of 18. Maybe there are 12 out of 18 of you with brown hair, and I want to pick 5 kids. Well, then I have to go to an 11 out of 17, and then to a 10 out of 16. These probabilities here, if you type them in, are changing a fair amount right here, where this is not going to end up being the same probability as this or as my 5th one right here. I have too small of a group, and my sample, like if I was picking 5 people, is too much out of that little group. But let's say I was, instead of picking 5 people out of my classroom, I was picking 5 people out of the St. Louis metropolitan region. Well, then I'm looking at like, I don't know, say 2 million out of 3 million people in the St. Louis region have brown hair. And then my next pick would be 1,999,999 out of 2, like this. And then I go to my next one. This decimal, almost identical to this decimal, almost identical to this decimal. When you have that big of a group, pulling one person out doesn't really make much of a difference at all. In our class, if there's 18 of you guys, 1 out of 18 is like 5% of the class right there that's been removed. That's a lot. But 1 out of 3 million is like not even close to 1% of the data. So it's like basically a matter of scale. And we use a condition to decide like where is the line in the sand? Where is the population, like the sample small enough with respect to the population that it's okay to pick without replacements? This is a condition we use a lot second semester in this class, and we're getting used to it now. It is called the 10% condition. So as long as the sample is less than 10% of the population, you can still assume approximate independence between trials. And the symbols we would use for this, we would say that little n, our sample size, is less than 10% or a tenth of big N. Big N is our population size. So if your sample is less than 10% of your population, you don't have to worry. You can still call it basically independent. So in my class of 18 kids, 10% of you guys is 1.8. So if I even try picking 2 people out of my class, that's too much. 2 is more than a tenth of 18. I couldn't use my 10% condition. But if I'm going to St. Louis, say I want to pick 1,000 people for my sample, 1,000 is still less than 10% of 3 million. 10% of 3 million is 30,000. So yeah, we could pick 1,000 people out of St. Louis and still be cool. So it's all a matter of scale, basically. And you'll see this 10% condition a lot in second semester. So let's talk about this example right here. So we're going to look at a bunch of different cereal boxes right here. And the cereal company puts toys in some of the cereal boxes. We've got SpongeBob characters going on, and you can see all their names written down right here. And we're going to say that 20,000 out of each of the 120,000 boxes is for each character. So the characters are evenly split. There's a sixth of the boxes having each of them. And this is our total number of boxes. If a person bought 8 boxes at random, what's the probability of getting exactly 2 Patrick toys? So you are picking a cereal box. And when you pick a box, you don't put the box back on the shelf and pick a second box of cereal. Like, you don't buy the same box twice. That doesn't make any sense. So we're sampling without replacements. But 8 is our sample size. 8 is less than 10% of all the cereal boxes. It's definitely less than 10% of this. So we have approximate independence. So we can still do binomial stuff, even though it's not technically independent if our other conditions are met. It is binary. You either get Patrick or you don't. The number of trials, we're picking 8 boxes, and the probability of success is a sixth. It'd be 20,000 out of 120,000. So when we go to set that up, X is going to be the number of Patrick toys, and X is binomial with N equals 8 and P equals a sixth. Again, we showed independence by verifying that 10% condition. And I'll just do this one on my own calculator instead of pulling it up on the computer here. I would want to do a PDF. We have 8 trials. Probability of success is a sixth, and we want to get 2 Patrick toys. If you do that, that's about a 26% chance. So the probability X is 2 is a binom PDF for this one, because it's equals. My trials were 8. My P is a sixth. My X value is 2, and I get 0.2605. So yeah, if you can verify the 10% condition, you can still do binomial stuff. Hopefully these are starting to get a little more comfortable for you guys. And then the very last thing on binomial distributions, we're just going to practice one more time with our mean and our standard deviation. The mean, I take my number of trials, which is 8. I picked 8 boxes, times a sixth, and 8 over 6 is 1.333. So I'll write an interpretation on here so you can have it to copy, but I'll just talk about it out loud. If you pick many, many sets of 8 cereal boxes at a time, so you're picking sets of 8s, you would expect to have an average of 1.33 Patrick toys in your set of 8s. So that's the idea right there. And then for the standard deviation on this one, you would set up N times P times 1 minus P, and then do the square root on that. So my standard deviation on this problem, I would do square root 8 times a sixth times 5 sixths, which is like 1.05. So if you have a randomly selected set of 8 boxes of cereal, the number of Patrick toys is typically going to deviate by about 1.05 box toys from the mean of 1.3. So I'll slap those answers up, and then we are done with our section. Okay, so here is our interpretation. Make sure you guys write these down. That's how you would interpret mean and standard deviation in the context of a binomial problem.